Hello, everyone. We're going to go ahead and go over section 11.1, which is on gathering and organizing data. So as an overview of college GPAs over the last 10 years have been getting higher and higher, and our students getting smarter or our professors lowering their standards. In order to answer questions like these, it's valuable to gather data. So it's important to gather data for questions that can come up like this. It's better to have more information. A lot of people could argue either side of a question like this. So it's good to have more information. And information could be things like having more readily information like by the internet and stuff like that. That can be like a huge part of this, as well as many other things. So a lot of the times we just need to gather more information, gather more data about certain questions. So starting off with populations and samples. So we say data are measurements or observations that are gathered for an event under a certain study. Statistics is the branch of math that involves collecting, organizing, summarizing, and presenting data and drawing general conclusions from that data. So when statistical studies are performed, we usually begin by identifying the population for that study. So identifying who do we want to study for this specific type of study. Then we say a population consists of all subjects that are under study. So the population is all the people you're studying. And a sample is a representative subgroup or subset of that population. So once you identify the population that you are studying, you can take a sample of that population to kind of represent the population as a whole. Like if we wanted to do a study where we asked all the people that lived in America, or like North America here, like all these sorts of questions, then a sample of that we would probably have to find, considering that we probably don't want to ask questions of like the millions of people that live within North America. That would be a lot of people. That's like considering like Mexico and Canada as well. So it's millions of people. We cannot possibly ask all of these people these questions or like conduct studies on all these people, but we can create a sample size, or a sample of the groups within the population that we chose. That would be a subgroup that would represent our population. So we could do things like taking samples, as opposed to using an entire population, because it would just be probably way too crazy, way too intense, way too hard to have everyone in the sample participate. So then we also leads us into sampling methods. So we'll study 4 basic sampling methods that can be used to obtain a representative sample. Some are sometimes better than others. So number 1, we have the random sample. So in order to identify or to obtain a random sample, each subject in a population will have equal chance of being selected. So everyone has the exact same chance of being selected. Nobody is more likely to be chosen than anyone else. 2, we have a systematic sample. So that is in order to obtain a systematic sample, each subject is given a number and every K number is selected. So that just means like every 10th, every 20th, every 100th number is selected. So it's just every like increment of people that will be selected. It's very similar to a random sample, but instead of a purely random sample, in systematic sample, it's more like everybody has the same kind of chance of being selected, but you are chosen in a very systematic order, as opposed to random being like very purely random. Then we have 3, a stratified sample. So in order to obtain a stratified sample, the population is divided into groups based on similar characteristics, and then members from each group are chosen at random. So there is still a randomness element into it, but they are categorized by very similar characteristics. And then people from each group are taken, chosen at random. So it does give you a little bit kind of better of a choosing because you've separated people by very similar characteristics and then picked from those groups, as opposed to like everyone having the exact same opportunity to be chosen. You could end up with a little bit of a skewed sample that way, depending on like maybe you chose more people of a certain demographic or certain characteristic than others. It was purely random, but maybe it wasn't that great of like a choosing. Then lastly, 4, we have the cluster sample. So in order to obtain a cluster sample, that would be an existing group of subjects are chosen, and then just used to represent the population. So cluster samples are typically not wonderful because you kind of just choose a group and then you're like, they're in charge of the whole population. Like they will present the whole population. This group was maybe not even really designed. It was just kind of chosen. So like a group that already existed, you just like chose them and made them representative of the population. So we have different sampling methods. Some are better than others, but these are the different sampling methods that could potentially be used. So as an example, a student is given an assignment to find out how late typical students at their campus stay up to study. We're going to decide which type of sampling method they are using for each corresponding scenario. There's going to be 4 scenarios, 4 options, so it makes sense. There'll be one of each. So for A, we have the student stops at the Union before 9 a.m. and asks the group how late they stayed up studying the night before. We want to identify which method this is using. So if we're thinking about the question, we're trying to find how late students typically stay up to study. So the person who's conducting the study shows up at the Union before 9 in the morning, sees a group of students, and just asks them how late they stayed up the night before. So this group of students was already existing. They were already together. They were already in the Union, and it was already before 9 a.m. So they were already there, and our person conducting the study just questioned them and is going to say that's representative of the entire student population. This is a cluster sample. This would be this group already existed, and you just asked them, and then they became representative of the entire student population. You're asking people that are awake, ready, and in a union, in a student union before 9 a.m. Those people probably didn't stay up very late, or they never went to bed, and it's one or the other. So these people are probably not a great representation of the student body. So like there. So like that's probably not a great representation because you're asking these people that are already like up and dressed and have eaten most likely and like they're ready. They've driven to the student union. They're already there. It's not even 9 a.m. They probably didn't stay up very late, with the exception being that they never went to bed at all. Maybe they studied all night and then came to the union. Which those are probably 2 extremes. So they're probably not great people to ask. So that would be a cluster sample. Then we have the student asked the school registrar to give them a list of 50 students whose student ID numbers end in a 4. This is blank. So in this situation, we have the student is at the school registrar, they're asking for this list, and then they're going to just choose whose student ID numbers end in a 4. Because there is a number in this case, there is a number 4. A lot of the time we want to think it's stratified because that would be every certain number of students. But as opposed to that, instead, like student ID numbers are typically like randomly assigned. So you're getting this list of 50, and then it's just being handed to you, and then you are just choosing anybody whose ends in 4. Since student ID numbers are typically randomized, and then you're getting a random list of 50, and then you are just choosing them, technically anybody with the last number 4, it was pretty like equal since the numbers were randomly distributed in the first place. So this would be an example of a random sample. So student ID numbers are assigned randomly, and then the 50 that just end in 4 are just chosen. So it's sort of an idea that like you could have been chosen really at any opportunity. And I think I misspoke before. This would be a systematic example there. But so now we're going on to our next 2. So see, we have the student surveys, the 5 people sitting closest to the door in each of the 5 classes. So in this case, like we're having these people, like they're all in class. So they have that in common. They have a common characteristic. They're in this class, they're either interested in it or they're required to be there. But either way, that's a characteristic. They're all in class. And then they survey the 5 people that just sit closest to the door in each of the 5 classes. So in this case, they're kind of choosing a group of people essentially randomly from a group that was already kind of grouped together with a characteristic. all of these students have to be in this class, but then it was just the 5 who sat closest to the door, which was the random part. That's how they were chosen. So it's kind of random samples within characteristic groups. And this is the stratified sample. So the stratified sample, students were chosen from a class, they had that in common, but then they were just chosen randomly based on their placement by the door. So that was kind of an example in that case. It was random, but based on people with characteristics. Characteristics being that they were in the class. That leaves us with our last one here. The student looks at the campus directory and chooses the first name on the top of each page. So this, it doesn't necessarily have a number, like kind of how we saw before, but we wanted to think that like the ID ending in the number 4, that might have been, you know, a certain type of method because it ended with this number 4, but we decided that that was just very random. But in this case, there's no number, but it's always going to be the top, like the first name at the top of every page. And that is systematic because that is just every time you turn to a new page, you are just taking the first name on the top of that page. It is random, but it's got more structure to it. Instead of just being like, I'm just gonna close my eyes and point, it's the top one at the top, or like the first name at the top of every page. So that one would be systematic. Names chosen based on them being the first name on each page. It's still, you know, very random because you don't necessarily know who's going to be on the top of every page, but they are chosen in a systematic way. So those are the 4 sampling methods. So moving into descriptive versus inferential statistics. So there are 2 main branches of statistics. There's descriptive statistics and inferential statistics. With descriptive statistics, we say statistical techniques are used to describe data. So in this case, we are just describing it. We're using statistics to describe. This involves gathering information about every individual in a population. So that would mean you need to ask every single person in your population that you chose. This is based on collecting, organizing, and reporting data without actually using that data to draw conclusions or any wide-ranging conclusions. So this is purely like you are asking everyone in this population, you are surveying everyone in the population, and then you are just providing that and like describing the data as opposed to making conclusions about your data. So there's 2 different types of versions of statistics. The first being descriptive, meaning you are just gathering this data, you are using it to describe that data, but you are not drawing conclusions. Inferential statistics is the drawing conclusions part. So it's the statistical techniques used to make inferences. It's used to make conclusions. It's based on studying characteristics of a sample within a larger population and then using them to draw conclusions about an entire population. So this is based on like taking that sample set and then surveying them and saying that based on the sample set, the whole population has these conclusions. So inferential statistics is definitely not quite as sound as statistics as descriptive statistics, since descriptive has to gather information about every single individual in that population. And then there aren't any conclusions. It is just, this is what the data says. With inferential statistics, you are choosing a smaller sample out of your population, you are surveying them, and you are projecting that entire conclusion to the entire population. You are using it with the goal of making conclusions or drawing conclusions about populations instead of asking every individual in that population. It's definitely a useful tactic when you have really, really massive populations. You know, if you want to ask everybody who lives in Northern America certain things, you would be really hard to ask every single individual who lived in Northern America. So instead, you would probably use inferential statistics. You would gain a sample size, hopefully a very good representative sample size, and then you would use them to survey and then use that to project to the entire population. So there are definitely 2 different types of statistics that we have here. descriptive versus inferential, basically. Are you trying to make a conclusion or are you not trying to make a conclusion? So moving forward, that leads us into frequency distributions. The data collected for a statistical study is called raw data. So all the data that you collect, no conclusions, not separated, not put in the graph, pretty picture, nothing. It was just raw data. In order to describe situations and draw conclusions, we would like to organize data in a meaningful way. So figuring out how to organize that data. Two methods that we use are frequency distributions and stem and leaf plots. So focusing first on frequency distributions. And there are two types of frequency distributions. There's categorical frequency distribution and grouped frequency distribution. Categorical frequency distribution is used when data is classified by a category, not necessarily by numbers. So that would be something like people who wear blue shirts versus people who wear red shirts versus people who wear purple shirts. It's categorized by like a specific characteristic. It's not the numbers. A grouped frequency distribution is used for numerical data to be divided into what we call classes. So this is an example we see on the side. We have number of pets and frequency. There's only one category. The category is number of pets. And then we break that category down into classes. So for example, for number of pets, we have 1 to 2 pets, 3 to 4 pets, 5 to 6 pets, and 7 to 8 pets. And then we can calculate the frequency of each one of these results. So this was a grouped frequency distribution. There was just one category that got broken out into groups and to classes specifically. Categorical frequency distribution is divided up into the different categories. But those are frequency distributions. It is typically going to be the classes or categories that we have and the frequencies in which they kind of arise in situations. So let's go ahead and try one out. So for example, we say a health food store recorded the type of vitamin pills 35 customers purchased during a one-day sale. Construct a categorical frequency distribution for the data. So this is a categorical frequency distribution. We will break this down into the categories of each type of vitamin pills. So the different vitamin pills we have are vitamin C, vitamin A, vitamin D, vitamin E, and vitamin B, and those are only the different options. So that's how we'll break up our frequency distribution into its different categories by the different vitamins that were actually purchased. And then we'll find its frequencies by how many times they appear in this set of data. Let's go ahead and do it together. All right, so having our example here and then having our data that we have, we want to make this diagram, this frequency distribution. When we make our frequency distribution, we're going to find the type or the different categories, and then we're also going to find the frequency of those categories. Since we're going to do this by hand, we're going to add a third column. We're going to make it the tally column so we can tally as we go instead of necessarily like counting every single one of them. We're going to tally them and then counting will come for the frequency portion that we have. So when we make this table, we can go ahead, we can separate it by type, tallies, and frequency. So when we have these, and we're going to make our little table here. We're going to go ahead, make our table. Like we said before, there's going to be a couple different types. We have type A, draw a line there. We have B for vitamin B. We have vitamin C. We have vitamin E. And we have vitamin D. So these are the different types that we have. And then we'll separate these portions here. Actually, that one should probably be a little farther away there. So maybe like that. There we go. So we have all of our different types, and then we can tally each one of those. Extend this a little bit. So we have type, we're going to start with A. So vitamin A. So let's go through and tally them up. So going across our first row, we see there's one A in there, so we'll put a tally. In our second row, we got another 1. In our third row, we have another. In our fourth row, we have 2. And then in our last row, we have 1. So when we added these up here, I realized I drew a little extra tally there. So when we actually made these tallies, now we can count them up. We have 5, 6, so the frequency is going to be 6. Then we can go on to B. So pick another color. So across our first row, there are no B's. Across our second row, there's 1. Across our third row, there are none again. Across the fourth row, there are 2. And then across the last row, there is another 2. So count those up. That's going to be 5. So now we can go on to type vitamin C. So across our first row, we're going to have 1, 2, 3, 4. So 1, 2, 3, 4. Across our second row, we have another 1. Third row, we have 1, 2, 3, 4. Across our fourth row, we've got another 2 here. And in the last row, we have 1 more. So our tally, we ended up getting 5 and 10 and 12. So our frequency for vitamin C in this case was 12. Now we'll go ahead and do vitamin E. So across the first row, we've got 1. Across the second row, we've got 3. Across the third row, we've got another 1. Across the fourth row, there's 1 more. And on the last row, there are 3. So I just realized that I wrote these totally flipped around. D probably should have come first, but oh well. We counted vitamin E next. So vitamin E in this case is going to have 9. And then lastly, we have vitamin D. Let's pick one more color. Let's pick purple. So vitamin D, it's going to be the last one. So we've got 1 here, 2, 3, and that's all. So vitamin D had 3. So if we were listing them in alphabetical order, technically the last 2 rows should have been flipped. But those were our types there. We see that we've crossed out all of the different types on our data. So that was broken down by the category. So we had category A through E, and then we counted up the frequencies of each category within the question. So there is our categorical frequency distribution table. Now, when we do group frequency, it will look very similar to this as well. We'll just have classes instead of categories. Let's go ahead and go on to our next one. So our next example, we have in a previous Math 120 class, students reported how much time they spent on their homework in an average week, shown in the data below. We're going to construct a group frequency distribution for the data using 6 different classes. So we've got all of this different information. We need to break down the classes, and we need there to be 6 of them. How we break down these classes is we're going to look for the lowest number and the highest number. So if we look at this data table, the lowest number that we can find is going to end up being 1. So 1 hour a week, typically. And then we want to look for the highest number that we can find. So looking in our data, the highest number that we're going to find is going to be 18. So considering our final number, it was 1, and then our largest number is going to be 18. If we actually count that on our fingers, we're going to count 18 different values. And so we want 6 different classes, meaning that we're going to divide our largest number in this case, which is 18, by 6. And so that means that every class will have 3 values in each one. So that's kind of how we can break down the different number of classes. Let's go ahead and do this one together. So for our example here, like we said before, the highest number that we have is 18. The lowest number that we have is 1. And like we said before, if we count this on our fingers, then this would come out to 18 different kinds of answers, like 18 outcomes. So for us, we have 18 outcomes, and we want to divide that by our number of classes, which in our case, we wanted 6 classes. So this creates 3 outcomes like per class. This will kind of help us kind of separate this out as well. So we're going to go ahead, we're going to move this we're going to move it over here. Doesn't quite fit. So we're going to go ahead and move this so that we can go ahead and create our table below. So we have 3 outcomes per class. So when we make our grouped frequency distribution, remember breaking this down by class. So we're going to write out, we're going to have class. Once again, we're going to do our tally. We're going to tally it out, and then we'll have our frequency. So we have our class, tally, our frequency. And so our classes, like we said, we're going to have 6 of them. So if we have 3 outcomes per class, we start at our very first value, which is 1. So 1, 2, 3. So 1 through 3 would be our first class. Then we have our next class, 4, 5, 6. So 4 through 6. Then we'll have 7, 8, 9. So 7 through 9. And that's the pattern we're going to have when we go through these. So we have 7 through 9. So also give us 10 through 12. 13 through 15. And lastly, 16 through 18. So we have all of our different classes. Then we'll go ahead and tally. And then we'll gain our frequency as well. So our class 1 through 3, this means that when we tally, we're counting up the frequencies of the number 1, the number 2, and the number 3. So starting off with our first class here, we're going to go ahead and we're going to count. So going across for the first row, we've got 1, we've got a 2, we've got another 2. That finishes off for the first row. So between the numbers 1 and 3, there was 1, 1, 2, 2s for a total of 3. In the second row, we've got another 1, 2 in there. So that makes 5 so far. In our third row, going across, we have 1 more. In our fourth row, we got 1, 2 more. And in our last row, we'll have 1, 2 more. So that tally, we get our frequency of 10. So for the class of 1 through 3, there was a frequency of 10 in that case. Now we can go on to 4 through 6, same way as before. So starting in the first row, we'll have 1, 2, 3 in the first row. In the second row, we'll have 1, 2. In the third row, we'll have 1, 2, 3, 4, 5, 6. Oh, too many. Then in the fourth row, we'll have 1. And in the last row here, we've got 1, 2. So for the class of 4 through 6, the tally will end up being 14. So it's definitely got the highest frequency as of the two that we got. Now for 7 through 9, same thing. So across the top row, we'll get 1, 2. Across the second, we'll get 1. Across the third row, we'll get another 1. Across the fourth row, we'll get 1, 2. And then across the bottom row, we'll get 1, 2, 3, 4. Which is another 10. So frequency from 7 to 9 hours, frequency was about 10. So now we can go on to 10 through 12. So 10 through 12, as always across the top row, we'll have 1. Second row, we will not have any in the second row. In the third row, we also don't have any. In the fourth row, we're going to get 1, 2, 3, 4, 5. And none again in the bottom row. So that's going to be 6. We're going to start needing some new colors here. So once again, we'll pick purple. So 13 through 15, same thing in the top row. There's a 1 there. In the second row, there are 3. In the third row, there are none. In the fourth row, there are none. And in the last row, there's 1 more. So this makes 5. Our last color here, let's go ahead and pick this like orange kind of color. So we've got 16 through 18. It's really just going to be all the ones that are left over in this case. But across the top row, there's none. Across the second row, there are 2. Across the third row, there are another 2. None across the fourth row, and 1 last one in that bottom row. To gain 5 once again. So there we have our grouped frequency distribution. So we had to kind of figure out the different classes. So we figured out how many classes there were going to be. We broke them down into 6 different classes, identifying that there would be 3 in each class. We tallied up, we just counted straight across, we tallied up our information, and we found our frequencies based on the data that we were given. So that's how you construct a grouped frequency distribution. So all right, let's go ahead and go on back to our lecture. So the other type of plot or the other type of table kind of information that we talked about was stem and leaf plots. So for stem and leaf plots, we said another way to organize data is using stem and leaf plots where the data value or number is separated into 2 parts called stems and leaves. For a 2-digit number like 53, the tens digit 5 is the stem and the ones digit 3 is the leaf. So something like 36, the stem is 3, leaf is 6. 72, stem is 7, leaf is 2. For a 3-digit number, the first 2 digits are the stem and the last digit is the leaf. So for like 138, 13 is the stem, 8 is the leaf. For decimal values, the whole number is the stem and the decimal is the leaf. So for something like 8.4, the stem is 4, the stem is 8, the leaf is 4. So really in any case, it's always the last digit in a value is the leaf, and whatever digits come before that is going to be the stem. So if a case where you just have one single digit, that's typically going to be like if you had 3, your stem would probably be like 0 and your leaf would be 3, typically in that case. But we use these stem and leaf plots because we see a lot of the time our data will be fairly similar. We could end up with quite a few of the same numbers that start with the same tens digit but have a different ones digit. So for example, we can look at this kind of up in the corner. we've got these numbers 15, 16, 21, 23, 23, 26, 26, 30, 32, and 41. So we look at all of our different stems and our leaves. So we have numbers in the teens, we have numbers in the 20s, in the 30s, and the 40s. So our stems will be 1 through 4. Our leaves, since we had 15 and 16, the stem is 1, the leaf is 5 to make 15. Stem is 1, leaf is 6 to make 16. So when we break down stem and leaf plots, it's kind of a way that we can write our numbers in a shorter sense. Same thing with the 20s. So our stem is 2. So the 1 leaf really means 21. The 3 leaf means 23. There were 2 23s, so we add another 3. And 2 26s, so we have 2 6s. And each one of these means 21, 23, 26. And so it's kind of how we break down our different values here. Same thing for like, this even says how to place 32 specifically. So you have 32, the stem is 30, the leaf is 2. So it gets written as stem is 3, leaf 2. We also had 30, so it was stem 3, leaf 0. Lastly, we had 41, so the stem was 4, the leaf was 1 to create 41. So that's how we do stem and leaf plots. It's a way to categorize a lot of our information quickly, and we can see maybe what tens or hundreds values or something like that had the most data, because it would be the one with the most leaves. So that's why we use things like stem and leaf plots. So for our last example here, we say gas prices have fluctuated wildly in the last few years, but from 1980 to 1999, they were fairly stable. The data below represents the average price in cents per gallon of regular gas during those years. Draw a stem and leaf plot for the data. So we have just a bunch of numbers here. We've got numbers like 119 and 131 and 86 and all these numbers in between. So we're going to create our stem and leaf plots for all of these different pieces of data. So let's go ahead and go on over to our notes. All right, so for this example, we see we have 2-digit numbers and we also have 3-digit numbers. So for all these digits, we want to identify the stems first, and then all of the leaves will be able to be filled in once we figured out the stems that we need. So if we look here, we see our first number, 119. Remember, the last number is the leaf. Every number that comes before that is a stem. So in this case, the stem is 11. For 131, the stem is 13. For 122, the stem is 12. For 113, the stem is 11. We see another stem of 11. Now we have a stem of 8, a stem of 9, a stem of 10. Another stem of 11, stem of 11, 11, 11, 11, 11, 12, 12, 12, 10, 11. Okay, there's a lot of 11s in there, but the lowest numbered stem we got was an 8, and the highest numbered stem we had was 13. So when we fill in our stem and leaf plot, we're going to start for 8 for the stems, and we'll finish off at 13. So when we make our table, we'll have stems and leaves. We'll draw our line here for stems and leaves. Let's try to draw that just a little bit better. Stems and leaves, and we will make that one longer there. And then we'll fill in our leaves. So our first stem we said was going to be 8. Then we had 9. 10, 11, gonna make that longer there, 12, and lastly 13. And then we have these spots here for our leaves. So we'll go ahead, we'll erase kind of all the marks that we left first. And now we can go ahead and write out our leaves. So starting with the stem of 8, we want to identify our values here that have a stem of 8. Basically numbers that are going to be 80 something. And there's only one, it's 86. So our leaf for 8 would be 6 to create 86. There was only one of those, so we'll go on to the next one. Now our next stem is going to be 9. So we want to find all the numbers that have the digit 9. And there's only 2, and they're both 90. So our leaves would be 0, 0. Even if it's the same number, it still gets listed multiple times. And actually, we don't typically put commas. We're not going to put commas in there. So 0 and 0 to create 90 and 90. Then we can go ahead and go on to 10. So for 10, we can look through and we have 100 and we also have 106. So for our leaves for 10, we'll put a 0 for 100 and a 6 for 106. Then we go on to 11. This is the one that has a lot. So our very first number, we have 1119, or 119. Then we have 113, 112, and 115. There's quite a few of these, so let's just go ahead and start with the first row. So we had 11, and then we had a 9, 11, and then a 3, 11, and then a 2, 11, and then a 5. So going on to the second row, we have 114, 113, 111, 111, 115, and 117. So we'll fill in our leaves for the second row here too. So we had 4, 3, 1, 1, 5, and 7. So there were a lot of leaves on the stem of 11 because there was 119, 113, 112, 115, 114, 113, 111, 111, 115, and 117. So there were quite a few leaves in that case. So now we'll go on to stems of 12, so numbers that start with a 12. So we have 122, 123, 123, 123. There's quite a few of those. So for our leaves for 12, we'll write 2 for 122, and then 3, 3, 3 for the 3 123s. Then lastly, we'll go ahead and do our leaves for 13. So we're looking for numbers of 130. And there was only one. We had 131, meaning our stem is 13 and our leaf is 1 to create 131. So that is how we create a stem and leaf plot for data. You're always writing the last digit as the leaf, and every number that comes before that digit is considered a stem. So you can kind of collect up your data based on those digits that it begins with. So like numbers that were 80 something, our stem was 8, and we could have had more leaves. For 90s, we had stem of 90 and then 2 leaves. Stems of 10 had 2 leaves. Stems of 11 had like 10 leaves in that case. Stems of 12 had 4 leaves. Stems of 13 had 1 leaf. So we can see kind of how many digits. For looking at our data, we can definitely see that the values of around 110 like to 119, those were very obviously like the most popular values. So we could say that probably like a safe assumption would be gas prices between those years were most often around 110 to 119 like cents per gallon. So $1.10 to $1.19 per gallon. So all right. That wraps up that example. Let's go on back to our lecture. And that wraps up our section 11.1. So in section 11.1, we learned how to define data and statistics, explain the difference between population and a sample, describe 4 basic methods of sampling, contrast descriptive and inferential statistics, construct a frequency distribution for a data set, and draw a stem and leaf plot for a data set as well. So there we go. That wraps up section 11.1, and I'll see you in the next one.